Is Professor Chris Habeck, that trained as a physicist in Germany and UK in 1990 and then switched to neuroscience as a postdoc. After some computational modeling at the Neuroscience Institute in San Diego, he decided to move to human neuroimaging analytics and has been at Columbia University ever since.
Well, I also want to thank the organizers. Do you know how the cursor works on here? Oh, yeah. Sorry. Early Monday morning.
It's not working, so I don't know. It's not working.
Yeah, I could try to use this one, I guess. Let's see what that works. Okay. It does? Sorry. Ah, yeah. Okay. Okay. Thank you all for coming. And I thought there would be 50 people or so showing up, so it's quite amazing. But now I'm a little more nervous. So in a way, my talk is going to be somewhat complementary to Simon's, because I think what I'm doing is really quite a bit simpler, and we're going to do some very simple sort of empirical investigations of sample size with some very sort of traditional, I call them shallow techniques, you know, just one-shot learning with principal components. And I give my acknowledgements first because I once forgot to thank my coworkers, and they were very upset. So in order to avoid this, I'm giving them now so that this can't happen again. So for the intro and the motivation, probably all of you are aware of a very powerful account of sobering statistical power that came out 2 years ago by Scott Marek. And I'm just going to show very selectively just one figure panel here. And you can see these were multivariate brain associations. And he compared the in-sample or the training sample performance on the coordinate there. On the ordinate was the out-of-sample performance. And you can see particularly here, he looked at brain structure and resting state functional connectivity with support vector regression. You can see, particularly for psychopathology, you can see these very sort of vertically elongated clouds that really give a very big hint of overfitting. So in other words, your training sample performance was much better than the out-of-sample performance. And so we're going to try to sort of take where Marek left off. Well, rather we want to look at it in our own data, maybe in smaller sample sizes, but just very simply, we're going to investigate the training sample size dependence on the out-of-sample prediction of several endpoints. One is age. We're going to use age as well as cognitive performance. And I think this is maybe what sometimes gets lost a little bit in this sort of more recent data science focus. We are still doing neuroimaging. It's not just prediction of an endpoint that we're doing, right? We want to find out what areas are involved in the brain for information processing. And the topographic composition of patterns we get are important as well. So we don't want to forget about them, you know. And then there's one more question that I think is very practical, and I've always asked myself this. Should you do meta or mega analysis? And, you know, just to explain meta or mega, imagine for a given, possibly really huge sample size, is it better to use the data all in one shot to derive your pattern or, you know, whatever analysis you use? Or is it possibly better to split up into little parcels and then combine the results of the analysis in the little parcels? Which one works better, right? Now, as I said, I'm going to give you only empirical answers with a little sort of very simplistic computational model. And there's one caveat I have to give also. I mean, we had a lot of discussion in this group. I'm going to talk about inter-individual covariance analysis today only. So arguably, this is not connectivity in the more orthodox reading. We're not doing any intra-individual correlations here. Okay, so the data sets I'll use, in a way, they're very simple. One is from our own lab at Columbia, where we have fMRI data for 3 fluid reasoning tasks. I'm not going to discuss these tasks very much. It's thought there's an underlying network that is operational through all these 3 tasks. We have 324 people, resulting in 972 task maps across the lifespan, and we want to predict task performance, so recognition accuracy, right? So this is a medium sample. It's still not population neuroimaging, but medium sample size. Then we also, for the structural data, we take the UK Biobank, and I sort of could curate a data set of 32K plus people from 66 free surfer ROIs, volume ROIs, age 44 to 82. And we could carefully choose age, sex, and education to be mutually orthogonal and also evenly balanced. So to predict age, there's really no confounding effects by sex or education. The analytic framework, that's my personal workhorse, but I'm going to try a few other very traditional techniques. But we're using the scaled subprofile modeling. I think another talk will talk about this in more detail. It's a form of PCA regression, and I always call it the simplest shallow learning technique. So there's nothing, it's a one-shot thing. There's no sort of iterative architectures of any kinds, and we're going to select PC sets with the Akaike criterion. And as I said, we're going to look at topographic robustness and prediction of the endpoint as a function of the training sample set. And we're going to do what Marek did also. We're going to have extensive resampling technique where we have training sets and a test set, and we randomly repeat our derivation many times in order to get an idea about the inferential robustness. So also, sometimes people want to hear more about this technique, but I'm going to go through it very quickly. We do PCA on our data array. Then there's a very simple brain behavioral modeling step where we use the scores of the PCs, and we do a brain behavioral, this could be cognition, it could also be age, right? We get regression weights, construct a pattern with these regression weights, and that's a real brain image. And in order to get inferential robustness on the pattern loadings, we could repeat step 1 to 3 on resampled data. You could do bootstrap, or you could subsample without replacement. And to check the correlation with behavior in any data set, even one that wasn't part of the training sample, you just take this pattern that was derived, prospectively apply it to the held out data and see how well does it predict. That's what we're going to do. Okay, so I'm going to have to move along a bit. Let's do this now for the volumetric data of the UK Biobank. And I, in a way, have a replication or test sample of 500 people. That's, in a way, arbitrary. I could take 1,000 or 2,000. I wanted my laptop to not crunch here. So we vary the training sample in steps of 200 to 4,000, right? Again, that's arbitrary also. It doesn't really change much. You could go out to 10,000 and you'll get very similar answers. And what you can see is now the age prediction in and out of sample. In red, you get the in-sample prediction, and in black, you get the out-of-sample prediction. And it's interesting, for this particular technique that we use with the Akaike subset selection, you see that initially there's a bump, and then it comes back down for the in-sample performance. And in the lower panel, I tried to quantify overfitting, where I subtract the out-of-sample R squared from the in-sample R squared, and you can see there's a little bump as you increase the sample size, and then you come back down to this plateau. And the fact is, there is a plateau here, so there's some irreducible noise sources, so just adding more data doesn't really seem to make much difference, right? That's probably not super surprising, but... And we could ask, is this our particular technique only? And one easy thing you could do, you could just do linear regression with these 66 ROIs, right? That's very simple, right? You have no problem of rank deficiency. And you don't get the overfitting effect bump here, but you can see that you also achieve a plateau beyond which there isn't really much change. There's always a small amount of overfitting, but adding more data doesn't really help you achieve a better prediction success. Now in the fMRI data, we have fewer data points, but we can take the replication test set of n equals 50, and then we also use the training sample size in steps of 100 up to 900. And maybe I didn't mention, we're doing this many times, or at least 100 times. Here I did it 345 times before I stopped it. And you can see again, you're leveling off in both the in and out sample prediction, and you see the overfitting effect again here. If we had more, I think in some other tasks I have more data, although the prediction accuracy is lower, you will also level off here. So there's no adding more data gives you no more computational gain. And here's just a few examples where you can see the overfitting directly. For a sample size of 100 and 500, you see here that the test sample performance is sort of always lower than the training sample performance. That's overfitting. Okay, so now to this, maybe some of you might say, oh, I'm not very surprised by this. You know, the premise you're investigating is somewhat artificial. You know, everybody knows that you're going to get to a plateau. Okay, but we can also ask, how about the meta versus mega idea, right? So again, it's somewhat arbitrary. Let's pick a training sample of 500 and 800, right? 500 here and 800 here. And now let's do our mega analysis in a way is what we've been doing all along, a one shot where we use all the data points all at once. But now let's do a sort of randomly subsample 50 times and just take 100 people, right? But 50 times out of these training sets and do our analysis again and then just average the patterns and see what you would get, right? And you can see first, if you look at the held out prediction, you see that the mega technique really does better than the meta technique for both. You can see that the sample size helps as you have more. You do get a little bit better. We haven't reached the plateau yet. But you see that the meta technique doesn't really help in terms of prediction, but it does help much in terms of pattern stability. So if we look at all patterns, we have 200 here. We look at all possible inter-pattern topographic correlations, you can see that this way of doing the meta-analysis really robustifies the topographic substrates. They're much more similar to one another, and you can see this here. The sample size boosts this also. Okay, and you can really, this is the only brain image really, but you can see you can really turn this into, you know, also make it more appreciable in a real parametric map. That's a Z map that you get for the case of 500. We take all these patterns, these 200s, and compute a Z map, and you can see that the meta-analyzed pattern is much more robust and much more stable. Okay. So again, also here, is it only a multivariate where you would have this issue, where you can just do, you know, traditional univariate predictive modeling, and something similar appears here too. So you always hit a plateau, and that's my summary and conclusion. Increasing the sample size doesn't really, at some point, it doesn't really seem to help. So it's kind of the flip side of the Marek idea. So you need sufficiently powered studies, but then at some point adding more, at least with this approach, doesn't really seem to buy you much, you know. So, and I stress the contingency. We're dealing with shallow methods, and we want, you know, a group level pattern. We're not doing anything individual, you know, we're not having a deep learning architecture. So it's just standard sort of run-of-the-mill analysis. And for the mega versus meta-analysis, I showed that meta-analysis didn't really seem to help with the out-of-sample prediction, but it really made a difference for the stability of the patterns. And so to connect this to a bigger picture, if we, you know, so as I said, the flip side of merit, if we have orders of thousands of observations, that's maybe necessary, but adding more won't do much. And I think Simon sort of hinted at this also. If you make the either training or test samples really big, but the effect sizes are fixed, you just get very, very, very large statistical significance, but you don't really get any real new insight, right? So that's kind of a very uninformative use of doing some of these predictions where you get, statistical significance that's really, really impressive, but as Simon showed, there's a lot of overlap and the effect sizes are really fixed. Then the meta versus mega analysis, I think that harkens back to the earlier point that there's a tension between prediction and explanation or detection. And I think it's good maybe to remember we're not just predicting things, we also want to find the best, we want to ideally fit the best model to get the areas involved in information processing. And good model fitting, meaning in terms of the true underlying process, means we want to minimize the bias, while good prediction is a product of both low bias and variance, if you look at the residual sum of squares. So it could be that even inappropriate models could give you better out-of-sample prediction. I think that's some aspect that's sometimes not appreciated, right? And I think I'm going to whip this real truth just to look at this a little more in detail. And I've stressed this is a conceptual model. It's not neurophysically realistic in any way, but just to see what happens with some very simple covariance structures. So let's assume we have a pattern of interest. That's my gold standard I put in, and I have 1,000 voxels just to make it tractable and easily runnable on my laptop. I could do all this yesterday. So I made the problem simple enough. So you have a pattern small v, that's a gold standard pattern we want to get out, and it's modulated by a cognitive performance variable, cog. We put some noise on the cognitive performance variable also, so the pattern is modulated. People are employing the pattern to the degree that they're doing well on the task. Then we're going to add just some voxel noise, right, where we have IID, Gaussian noise everywhere in the brain. And then the last thing, and that's maybe crucial, and you'll find that all my results will hinge on this, these are correlated sources of activation in the data. Let's assume there are background things going on. Some of them have to do with physiological processes. Some of them are always there, but they're not task-related. And we have patterns in the matrix V, and then we have the mixing matrix or score matrix W. And you can vary the number of patterns. It could be very few, it could be quite a lot. And we're going to play with this parameter. We're going to set, in a way, the noise parameters here in the Gaussians. We set them arbitrarily, right? As I said, it's not so much neurorealistic. I just want to get a feeling what happens with this covariance structure. So we fix them, these noise parameters, and then we do the same split sampling scheme again. We have a training sample of 1,000, a test sample of 500, and we vary the number of nuisance parameters. And when you do this, you see, for instance, if you have 20 nuisances, also correlated activities in the data, you can see that the meta technique now does better than the mega technique for behavioral prediction. But once you add more and more nuisances, you find that this can flip around. All of a sudden now, then splitting things up into little parcels in the face of these correlated nuisance activities, it doesn't help anymore, right? And we can do this systematically, vary the number of nuisance pattern in the data. You can see that there's this crossover, and at some point, the meta techniques doesn't really work any longer, right? And we could push this out. You could do this, once you have 1,000 nuisance patterns, you basically have generated voxel noise again. You can see that at that point, the two will converge, but somewhere in this intermediate range, there are disjunctures. And again, I said this is not neurophysiologically realistic in any way. It's just to show what happens with very simple covariate structures. So I want to thank you for your attention. If any questions?
We have been receiving a lot of very interesting questions, but for the interest of time, I think we're going to have to let the next speaker. And if you have any questions, you can come and talk to us right after the talk during